I'll quickly introduce you. We are just across the Bay Area, I believe. So we moved from Stanford to Berkeley. Nitash Balsara is professor for electrochemistry at the University of California, Berkeley. And he will be talking about the mapping of energy density of batteries and fuel cells. Nitash, the stage is yours.
Yeah, thank you. Can I assume you can hear me?
Yes, we can hear you fine.
Okay. Yeah. Unlike the last two talks you heard, this will be a very ancient talk, and in fact, I was uh, asked by the organizers. They made up my presentation title, and I just honored that and went with it. And the organizers of this conference saw this paper that I had published in the Journal of Chemical Education. So this is a journal that you read if you're an undergrad. It's aimed at undergraduate education, written with me, my colleague John Newman, and we said here how we can compare the energy content of fuels and batteries in particular. So we have uh, batteries like lead acid and lithium ion energy density per kilogram. um, and of course, a battery weighs a certain amount, and you can readily see how many watt hours you've made. So there's no argument about how you do these a battery. But in a thing like octane, you use it in an ICE, and you burn it, and So how do you compare the two? And what we present is an apples to apples way to compare various energies, and this plot is not surprising that the energy densities of that we are used to in transportation are much higher than the energy densities that are used in cell phones and even in EVs today. So, so I'm going to leverage this presentation, this talk, I mean this paper, and address the issue of comparing batteries and fuel cells. So the first point I want to say is that it's based on thermodynamics, and thermodynamics starts with some calculation of free energies of formation, and many of them were done 100 years ago. So unlike what you heard in the last talk, things coming out in the last 5 years, this is old data of what the free energy of formation of carbon dioxide and things like that are. And I just put together the relevant free energies of the substances we were interested in drawing, mostly from 100-year-old papers, but sometimes more recent papers. And then there are some values like lithium sulfide, Li2S, where there is no experiment for surprisingly an old compound. So, so these are all. This is a value that we get from some simulations coming out of the University of Texas. So anyway, I'll come back to that point later. But uh, uh, yeah, so if you know the free energies, you can calculate how much energy you're going to get from a particular operation. All you have to do is to postulate a reaction. And here, for example, natural gas or methane is burned or octane is burned. And you can see that for the same amount of oxygen used, you would emit less CO2 if you burn methane than octane. Everyone has known this. And why these funny coefficients appear in these, you have to read the paper, but it's just undergraduate thermodynamics. Um, and so, on the scale of energy containing materials, carbon monoxide is on one side, lithium metal is uh, here, hydrogen, the fuel cell uh, does use the highest energy per kilogram of material known to man, or the periodic table can allow us. So, we can take these calculations and try to see what the carbon footprints of various technologies are entirely based on thermodynamics. So it's not based on data, assumptions, policies, etc. What does thermodynamics tell us? So that's the point that this talk makes. Um, the ICE engines have an efficiency of 35%, while stationary power has 43%, and that's just a matter of scale. If you have a small engine, you can't quite operated as